Hello, guys. Welcome to episode 3. We're going to look at the math underpinning Benford's law. Okay, let's go. So, I'm supposed to be an image here. But I don't know, it didn't load. It's kind of annoying. Anyways, um, so our brains think linearly, so obviously 1, 2, 3, etc. But nature grows logarithmically. Ah, consider a city with a population of 100. To reach 200, it must grow 100%. This takes a long time, during which the city stays in the 1 category. However, to go from 900 to 1000, it only needs to grow by 11%. The city passes through the 9 category much faster. So basically, because of our monkey brains, we think linearly, but everything is probably more logarithmic, looking at the grander scheme of things. So, although we see that probably all numbers should be seen in the world, in data, in nature, the same amount of times, roughly, it's actually not that way. Um, it's one, because as you can see, when something goes, I guess when things get bigger, they tend to stay at one more. Let's try to think of an example. Well, I guess an example would be if you're counting from 90, if you're going from the 90s to the hundreds, um like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have one, you have the ones, one, then you have the tens, the teens, then you got um you got the hundreds. So if you were to count from 1 to 100, one probably has the most numbers of all the numbers, just from in a smaller scale. So just imagine that you were just taking like random measurements that could be like up to the hundreds of thousands. The same trend would sort of happen if you're, yeah. I guess I could, yeah. I guess it's an example. It's bounded by 1 to 100, but it still holds. Um, yeah. So this is the fundamental formula. Um, The probability the number starts with the digit b is defined by the following formula. Log base 10 of 1 plus 1 over d. Very cool. So a d is obviously a number between 1 and 9 inclusive. And this formula dictates that approximately 30.1% of numbers start with 1, while only 4.6 start with 9. This is not an approximation. It is a mathematical consequence of how scale works. So as you can see in this graphic here, we have the amount of times different digits occur and just follows curve. So it would be like a bell curve. Well, it's not really a bell curve. It would just be like a half of a bell curve, basically, starting at 1 up till 9, decreasing because of the way things scale up, I guess. The principle of scale invariance got a really funky image, hippie. One of the most profound properties of Benford's law is scale invariance. If a set of river lengths in meters follows Benford's law, it will follow it just as perfectly if you convert every single measurement into inches, miles, or even light years. Because the law is based on the mantissa of the logarithm. Multiplying the entire dataset by a constant does not change the distribution of the first digits. That's working. Yeah. Okay, so let's talk about what mantis is. So when you're taking logarithms of a number, you have the integer part and the decimal fraction part, and the mantissa is the decimal or fraction part of the logarithm. So when you're converting between different measurements from meters to inches to feet to yards, wherever it is, um, you multiply by a fixed number. But when you multiply by this fixed number, it um, doesn't change the actual scale of Benford's law. So the sort of percentages of the occurrences don't aren't affected. This is because, so if you just go back to the formula here, the formula is log base 10 of 1 plus 1 over 1d. So if you were to multiply um, the number, which is inside of the logarithm, so let's say you had log c, log base 10 of c times x, that would be equal to log base 10 of c plus log base 10 of x due to log laws. So what this means is that it sort of shifts it would just shift the scale by a certain distance. It's sort of similar to coding in statistics where um, it it doesn't affect. So if you were to have like runners in a race and they're a certain distance from each other, and you say um, every runner moves 50 meters forward, the distance between the runners hasn't changed. So it's similar to that in that way. It's kind of hard to explain or to get your head around. So maybe I think I might have to do more research and um, come back to this to explain it better. Okay, so Benford's law is not a human work of using base 10. It's a fundamental property of numbers themselves. The law generalizes to any numerical base b. The probability of the leading digit d in base b is log base b of 1 plus 1 over d. So it can be for any base, it's the same. Um, yeah, the base is variable, so it's not just base 10. It's not only log base 10, it could be log base 16 or whatever. It if a data set is Benford, it remains Benford. Whether you look at it in decimal, octal, hexadecimal, it confirms that the pattern is universally constant for mathematics, independent of our chosen counting system, which is kind of ridiculous to think about. That this law transcends counting systems. Very interesting. And that'll be all for now. In the next video, we're going to look at more of the applications of Benford's law. I think I'm going to come with a video towards the end of this series, trying to explain scale invariance in a more in-depth manner. See you guys in the next video.